So if you're like me, and I'm into physical science, I catch myself interchanging the terms mass and weight. They are different. Mass basically is the amount of matter an object has, and in F is equal to ma, of course that's Newton's second law. The force applied to a particular mass will result in acceleration. M there is mass, the amount of matter in an object. Weight is something different. Weight is something we weigh ourselves in the morning. We step on a scale, and basically what we are doing is coming up with the force that we are exerting on the earth, okay, due to the pull of gravity. And the reason we exert that force on earth is because of our mass. So here we go. When you're stepping on a scales, okay, that's the equation you're using. The weight here, W is your weight. Okay, your weight is equal to your mass times the pull of gravity. And actually, the pull of gravity, the little g there is going to be your 10 meters per second per second. So, or 10 meters per second squared, or 9.8 meters per second squared. That's your g. So they are not the same. Put another way is that actually if you were to go on the moon, your mass would be the same, but your weight would be different. On the moon, it has a different g. Okay, this is different for on the moon. So that's how that works. And then I have a little example here to kind of show you how the acceleration and weight work together. So for instance, here we have kind of three scenarios. We'll call them scenario A, B, C, and D. And of course they involve an elevator. And in this elevator we have a guy standing, and notice that here the elevator is not moving, okay, or moving or at a constant velocity. So V is constant. And if V is constant, that means no acceleration. Acceleration is equal to 0. So in that case, notice that the scale works just fine. And up here, it's kind of interesting. He weighs about 140 pounds. Okay, so again, what that scale is doing actually is coming up with a force that he is exerting on the earth due to gravity. So here we go. Now notice that in scenario B, it's accelerating upward. So now we have actually an additional acceleration, and so notice his weight goes up. And in C, he is accelerating downward, and so here we have less acceleration, and so his weight goes down, acceleration due to gravity. And here we have, and we're going to talk in the next slide just a little bit about what we mean by free fall. Here we go, basically the thing has been cut, and notice that he cannot exert force on the scale. So the scale basically reads 0. So weight and mass are not. So here we go. Here's one for you. I like this little animation. See what you guys think. It's not animation, but think of that little person who climbs this ladder, okay, and he steps off. So notice in the first case, okay, I guess I'll call that A. How's that? Okay, let me go. Call this A. In the first scenario, A, he just kind of walks off and he falls to the ground. Now in B, okay, he's going a little bit further, okay, and so he falls to the ground a little bit further away from the Earth's surface. And in C, notice he got smart, and we went ahead and he got very much a running start, so he's going on that ramp, he's got a backpack, okay, and so, he's got a jet pack, okay. And I have a student in my face-to-face class says, can you really do that? And I don't think you can, but it's tempting, right? And so basically he leaves the earth, okay, he falls, okay, he's pulled due to gravity, okay, going to fall down, but, and maybe this isn't a good example, he basically, as he falls, he misses the Earth. Okay? He just misses the Earth. So that's why we say he is actually in orbit about the Earth, and he is what we say free falling. Okay? He's got a trajectory going this way, and the gravity will pull him this way, but the resultant is he basically just keeps on moving. Okay? Newton's first law of motion says that he's going to keep moving in the same direction with the same speed unless acted upon by an outside force. The force of gravity is acting upon him. That's why it's not a straight line. It's a curved line that we call an orbit. So it's really, orbits are just an ongoing free fall. Okay, so when folks in the space station, you might have seen videos of them up there, and they look like they're floating around with zero gravity. Actually, they have gravity, or they wouldn't be in orbit. If they're in the International Space Station, they would not be orbiting the Earth. It's just that they are in an ever state of free fall.